Hi, everybody. Good morning, good afternoon to everybody that is here with us on this second day of our webinar Facing Climate Change Towards Sustainable Coastal Cities. So we will today have three presentations of Alejandro, Talia, and Francisco. So with any other introduction, we will start with Alejandro. I will be presenting to you. He has a PhD in marine science focused on wave aquatic canopy interaction and currently awarded with the National Center for Spatial Studies postdoctoral grant in the Mediterranean Institute of Oceanography in France. He will present us surface current analysis in the southern coast of France by using high-frequency radar, wind, and wave modeling. So I leave the floor to Alejandro.
Hi, how are you? Thank you, Veronica, Valeria, and Rodolfo, all of you for having me today and inviting me. So do you hear me well, and can you see my screen so far? Hello? Do you hear me? Hello?
Yes, we can see you and hear you. Yeah.
Okay, so do you see my screen now?
Yes.
Okay. So, well, nice to meet you. To people like, I guess, I don't know if I know everybody, but most of you, I've seen you 5 years ago when all of us were together in Cancun for the amazing summer school. The 2 weeks we were having fun and learning a lot. So hello to everybody. Well, as Valeria said, I'm Alejandro Cases, EUCE. I have a doctorate degree in marine science. I was basically working on wave-seekers interaction processes, particularly Kelvin-Helmont instabilities. But nowadays, I've been working on a bigger scale, basically regional scale in the Mediterranean Sea. Basically, my project is founded by the National Center for Spatial Studies here in France, CNES, and the Institution for Mediterranean Studies, MIO. So the presentation that I'm going to talk to you about today is the analysis of surface currents from high-frequency radar systems, wind and wave modeling. Okay, so I'm just going to start a little bit with some kind of reviews, just to get familiar with the information and the theory and the background behind the topic we're going to talk about. So basically, currents in the oceans is the topic I'm going to discuss today with you guys. So basically, as you can see the picture here, currents in the ocean are quite complex. So it's basically the resulting process of many forcings such as the sun, precipitation, the wind stress, interchange of masses of earth and gases between the surface of the sea and the atmosphere, wave breaking process, evaporation process, changes in the salinity and the density and the pressure. So many processes are involved in this resultant physical mechanism, which is the surface currents. And normally this system is usually understood and modeled by using the Navier-Stokes equation, which is this complex equation we can see here. Normally we know this equation, this equation is based on the Newton's second law, which is basically the resultant of all the external forces are equal to mass times acceleration of the flow. So in general, all the total forces that we have at sea, especially at the surface of the sea, can be classified in these four main topics. One is geostrophic currents, which are basically the balance between the pressure gradients in the sea and the rotation of the Earth. We have also the wind-driven currents, which are basically produced by a balance between the rotation of the Earth and the wind stress. But also we have tidal and inertial currents, which are a balance between the gravity forces, body forces, and the pressure gradients, but also the bathymetric effect. So the bathymetric is also affecting quite a lot how the circulation patterns are featured. So why do we study currents in terms of global change? So we know that the surface currents at sea, we can decompose these in two main components. One is the geostrophic currents, and the other one is the non-geostrophic currents. So as we already know, geostrophic currents is the resultant from the balance between the pressure gradients and the rotation of the Earth. So from now on, everything which is non-geostrophic is something related to wind, waves, tides, and bathymetric effects, but not to the balance between the pressure gradients and the rotation of the Earth. So in general, now going to the topic, marine debris accumulation in the ocean is mainly ruled by the resultant geostrophic currents, while oil spill, search and rescue, and all these short-time processes traveling and flowing on the surface are ruled by non-geostrophic processes. So this is how and why it is important. So as you can see here, we have the two big island patches in the Pacific Ocean, the two big garbage islands in the Pacific Ocean. And also what you can see below is a picture of search and rescue from a Nature paper, where they were basically analyzing how non-geostrophic currents could be used to kind of develop some kind of forecast whenever the countries have to rescue people at sea. So this is why it is also important, the study of the surface currents at sea. So just a little bit of description. So what do we have in general? I'm going to talk about the ones I'm working here in my postdoc, but we know we have more ways of recording surface currents. But in this case, I'm just going to talk about the devices that we use to measure at big or medium scales in terms of spatial and temporal scales. So temporal scales of the surface currents are observed by using mainly remote sensing systems and also using numerical models. So as a remote sensing system, we have satellites, we have HR radar or high frequency radar systems, and we have numerical modeling. So as you can see here, this picture by Shelton in 1994, normally the blue line, which is numerical models, are very detailed. We can go from small to mesoscale activities, from minutes to several years. High frequency radars is a little bit overlap, which is going from the scale of kilometer to mesoscale or a little bit more synoptic scales, and also can be presenting information from hourly time scale to decadal time scale. And we have satellite information, which is the one which is covering the most of the domains in terms of planetary scale. And is mainly between synoptic scales in space, almost to planetary scales, and is basically presenting information from weekly to decades time scale in terms of time. So we have advantages, pros and cons when we are dealing with these means of recording or modeling surface currents. So for example, satellite information is very good because we can cover very big and very large space areas, but it's low resolution. And also we cannot have very detailed information at the coast where most of the human interaction at the sea is occurring. High frequency radar almost is very close to the coast. Normally we can have some devices going a little bit further, but mainly is in the first 80, 100 kilometers away from the coast, and as close as 2 kilometers from the coastline. It has a high spatial resolution and temporal resolution, but also can provide information in the coastal region. So, and now numerical models. So numerical models are normally great. However, we have two main needs when we are dealing with numerical models. Normally, one is very high computationally speaking to solve many scales. When we are trying to solve the interaction between the atmosphere and the ocean, going from when you want to model one and going to several scales and the interaction between them. And also, most of the time, you need field information to apply calibration and validation. So, what we try to do is, as we have all this information, why don't we combine them? Why don't we try to use the best of all these data sources in order to try to analyze how the surface currents in the Mediterranean, the northwestern Mediterranean is? So for this, we basically combine information from satellites, from high frequency radar systems, and from numerical models for the surface current analysis. So basically, I'm going to explain a little bit about what HR radar system is. So basically, we have a set of antennas. I guess Francisco is gonna give you a little bit more about these details from the SOCIP, which they have a lot of experience. But a little bit description is basically we have a set of antennas emitting some kind of waves, and these waves have a specific frequency. So when the wave reaches the surface ocean, they go back, and when you measure this return signal, you will see there is a shift in the frequency. So with this shifting in the frequency, you can estimate the surface currents. So with the satellites, what basically the satellite does is able to estimate also according to some kind of Doppler effect the level of the sea surface. So according to this and according to the geostrophic theory, you can estimate how the geostrophic is. So and we use these two in addition to numerical model to try to combine them all together, as I told you. So as we already know, we can separate the total surface currents in geostrophy and ageostrophy. So the geostrophy is basically monitored by the satellites, and using the HF radar system, we were able to also estimate the ageostrophy according to these two additional computation, which is the wind-induced currents using a very simple Ekman model, where the Ekman model is a function of the wind stress and the direction of the wind. This is estimated by using atmospheric wind models, the WRF, and the Stokes drift. Basically, what we did is, or what we do is, we simulate the wave field in the full Mediterranean Sea for 50 years, and we try to downscale this at the coast. In this case, this is a zoom in the place where we are working at, which is the Toulon Bay, which is nearby Marseille. And according to this, we can estimate how is the Ekman wind-induced currents and how is the Stokes drift, which is basically the contribution of the waves to the total surface currents. So, going back a little bit, as a theoretical background, I can show you here is the high-frequency radar system we have here in the Toulon Bay. So this is the region. Is roughly speaking is about 1 kilometer square. Has a resolution of about 1 kilometer and also has 100 kilometers square, sorry, and has a resolution of 1 kilometer and is giving you information hourly. So if we use the HF radar system and we assume that the HF radar system is recording geostrophy, is recording wave, wind-induced currents, as I told you before, these components, is also recording tidal and inertial components and bathymetric effects. So we can assume, or we can infer that the surface current is basically recording the total surface currents nearby the surface region. And if we go a little bit further, we can say that between this total surface current, which is decomposed in the geostrophy and the non-geostrophic current, the non-geostrophic current can be decomposed into the Stokes drift, which is the one produced or induced by the waves, the wind-induced current, which is produced by the wind stress at the surface, and more nonlinear effects, which are basically mesoscale or submesoscale, which are transported from the open ocean sea and normally are advected into the local region. So and the question is, okay, how can we do this? How can we try to understand all these mechanisms, all these data sources, and how can we interpret this in a smart way to retrieve or to isolate several components from the surface currents? So what we did was basically we combined the HF radar system, as I told you, along with the numerical wave modeling and satellite information, initially to estimate the geostrophic component. So because if we are able to estimate the geostrophic component from the total surface currents, we are able to subtract the non-geostrophic component. So how? We combine the data. Basically, we use an unsupervised neural network, which is called self-organizing maps. So this is an unsupervised neural network which is able to learn from the data and it's basically suitable for extracting nonlinear processes according to the size and the nonlinear processes involved in the data per se. So basically, in addition to this, we use something which is called the non-divergence or the divergence estimation of the velocity field, because by definition, by theory, the geostrophy is always non-divergent. So as you can observe here, basically we use the combined information, the HF radar system as input data, here named as combined measure data, which is the velocity field from the HF radar and the wind information. And after that, we were able to estimate or identify features. So initially, as we were focused on the geostrophic estimation, you can observe something here on the right, which is the red arrows are the wind and the black arrows are the surface currents. So as we were trying to find geostrophic components, we are expecting that under geostrophic dominant systems, the wind is basically negligible. So if the wind is basically negligible, we can expect that the balance in the surface current or the resultant surface currents is basically the balance between the pressure and the rotation of the Earth. So as you can observe here, we were able to do this. So the red arrows, which are the wind, are basically negligible, while the black arrows are dominant and basically are balanced by the geostrophic system. But not only this, we needed to estimate this. So how can we estimate this? We again use satellite information, but in this case using resultant satellite information, which is specifically providing us information from the geostrophy. and comparing this in time and also in space. So we use from the Copernicus database 11 different satellite missions, the ones you can see here. They are very well known, and also spatially speaking. So let's go initially to the temporal analysis. So we took basically 3 points along the vertical axis or the latitudinal axis of the HL radar system. So to see if we were able to capture this geostrophic feature in the full HL radar system. So what you can see here is when we have no winds, remember we are expecting to have a dominant geostrophic system. So as you can observe, we have the red squares and lines are the geostrophy estimated from the HL radar system using the unsupervised neural network, while the black triangles are the satellite derived geostrophy, which are basically measured geostrophy. So we were able to capture this, the magnitude of the geostrophy, but not only the magnitude, also the seasonality. So as you can observe from June, which is the summertime, up to mid-fall, we have a weaker geostrophy, while when we start the late fall until the starting of the winter, we start to see a stronger geostrophy. So, and also to check this, we were expecting to have a strong influence from the ageostrophy, which is non-geostrophy, when we have windy patterns. So as you can observe in the lower panel, you have again the red lines are the surface currents, and the black line on the circles is the non-geostrophic component. So when we have wind, in fact, indeed, we have a strong non-geostrophic effect from the wind specifically, and from the waves. So according to this, we said, okay, we seem to be capturing well what is happening in terms of separating the different components of the surface, the total surface currents. So, and according to this, we said, okay, what if we can see what is happening a little bit forward? So we compare here information, spatially speaking, on the image on the right side. So you have the HL radar system, which are basically the geostrophic estimation from the HL radar system with a red arrow, while the satellite geostrophic information with a black arrow. And what we can observe is indeed we were capturing quite well the direction, but also the magnitude of the geostrophy. And in addition to this, as I told you before, satellite is not able to provide you information very close to the coast, while the HL radar system can do that. We were also capturing additional features like these vortices produced by the land constraint in the region. So we said, okay, it looks like we are capturing what is happening. So according to this, we were able to make us to make ourselves more questions. For example, what if we apply the estimations of the geostrophy according to different months, and how this is compared to standard methodologies to estimate geostrophy? Normally, the geostrophy is estimated using standard average. So what we say is, okay, if we have a neural network which is able to give us more information, what if we are able to estimate the seasonality, as I showed you in the time scale, but in this case in the spatial scale, the seasonality of the geostrophy, and we compare that to the standard methodologies to estimate the geostrophy. So as what you can observe here is again the geostrophy between the read from the HL radar system and the geostrophy from satellites. And on the left you have the standard estimation, and on the right you have the conditional estimation according to the neural network. So as you can observe, the standard estimation is basically tilted southward compared to the information from the satellite, while the ones using a conditional average is better capturing what is happening in the site. Not only far away from the coast, but also in the place where we have the strongest geostrophic resultant current. And in addition, we are providing better information very close to the coast. So, and after that, we said, okay, what if we go a little bit further? And if we are able to say how important is the rest of the components, so the non-geostrophic components, when we are trying to see compared to the total geostrophic current. So is it the geostrophy always the only one which is dominating the system, or the non-geostrophy is also contributing and doing something on the resultant current? So to do this, we basically, once we calculate the geostrophy, we are able to remove the geostrophy from the total surface currents. And according to this, we are able to perform direct estimations of the wind-induced currents. So remember that part of the currents, the resultant currents, is also produced by the wind stress. So if we do this and we remove the geostrophy, we are able to estimate a wind-induced currents as a function of the wind stress. So what you can see here on the right figures is basically a linear function which has been found according to the non-geostrophy components resultant from removing the geostrophy from the data. So in general, this linear fitting is actually adjusted very well. It's around 0.98. And basically what it says is, it says is that the wind-induced currents at the surface is a function of the shear stress, and according to 0.84 times the shear stress. According to this, we are also able to estimate how close or how is the deviation or the deflection of the angle, because when you are estimating surface current from wind, the classical theory says that if you use the classical Eggman model, the deviation of the surface current with respect to the wind direction is 45 degrees. So one of the questions that we wanted to answer is, okay, is it the 45 degrees? Because nowadays the scientific community is basically discussing about this, and there are a lot of researchers saying, okay, this is not true, this is true, this angle is below, this angle is above. So what we were able to find is, in fact, the angle is not 45 for sure, but the angle is between 18 and 23 degrees. So what is basically saying this linear model is, okay, when the wind is blowing, the wind response, let's say, in around the magnitude of the wind basically is 0.34 times the shear stress produced by the wind stress, and the deflection of the surface current with respect to the wind direction is in between 18 and 23 degrees. And after that, once we were able to estimate the geostrophy, we were able to estimate the contribution from the wind. If you remember the very first figure when I was basically listing the main components in the total surface current, we still have to say, okay, how important really is the contribution from waves? When I mean contribution from waves, it's called the Stokes drift. And to do this, you can see the lower panel, which is a linear regression. You can see that the red dashed line is the one without the squares, is the linear fitting previously introduced, while the dashed red line with the squares is superposing from the numerical wave modeling the Stokes drift, and trying to see how important it is when we just superpose it. So according to this, you can observe that when we have this vertical black dash line, and we have wind speed less than 6 meters per second, the contribution from the Stokes drift can be assumed negligible. Why negligible? Because the non-geostrophic component, when you superpose the Stokes drift, is less than 10%. But as far as you start to, or the system starts to increase the wind speed going above 6 meters per second, the contribution from the waves starts to be really important. So can even go up to 20%, the non-geostrophic component. So this normally is not taken into account when you are trying to simulate the surface currents at sea, and has to be taken into account. So just to let you know up to this point, and now I want to talk about something that we are doing, and it's based on the new space missions that the French government wants to launch, and it's basically trying to combine all this information, but in this case to retrieve total surface currents, but directly from the satellite, like not only geostrophy but the total surface current. So basically what we are doing is combining available information from satellite, again, HF radar system, models, but in this case trying to retrieve this total surface current instead of just the geostrophy. So how basically we have the SAR images, which are images from the Sentinel-1 mission, which are 1.5 kilometer resolution. This information is available. This information is from the SAR are the only space mission which is able to work during day and night, even if you have rainy time or you have a cloudy time. So if you are able to clean this information, so initially you have this initial information, which means radial velocities, which are total radial velocities with respect to the track of the satellite. You can correct this information to remove all the pollution on land. So you can see the corrected radial velocity is in this case corrected here, where you can see now all the black arrows, the black area is the land. So, but up to this point, the state of the art says that, okay, we are able to measure from satellite information the total surface current, but in terms of radial velocity, so with respect to the trajectory of the satellite. So we started to think about how can we solve this problem. And the best way we thought we could try to solve this problem is again using numerical model and in situ information. So in this case, we are using all the HRS system available in the Northwestern Mediterranean Sea, including the SOSIP-1, which Francisco is going to introduce you later, and also information from the big Mediterranean Sea, the numerical information, the surface current from the information available in Copernicus, which are normally validated and corrected using in situ data. So we can say that this information can be quite trustable in order to do this retrievement. And how? There are new methods of using artificial intelligence. So for example, in this case, instead of using unsupervised neural network, which are basically techniques used to classify and identify features, we are using now supervised neural networks, which is called convolutional neural network. And basically what we are doing with this convolutional neural network is to use the convolutional network as a transfer function. So you can present to the neural network the radial velocities from the SAR images, and you can use the numerical models and the HRS system as patterns to make the neural network to learn and to understand how the system is. So you are able to retrieve total surface currents in a Cartesian projection just using SAR images. And according to this, we can in the future be able to analyze transport process features at sea. So I just want to thank you and to give you some very brief conclusions. So at this point, we are basically opening new avenues for data fusion coming from pre-existing databases to obtain just oceanographic variables in a higher spatial resolution, as for example, the one using the HRS system or using the new SAR images. The use of artificial intelligence, in this case, deep learning method for data fusion, especially using remote sensing, measured data, numerical information, are needed for the new incoming SWAT, which is a new space mission is going to be released, and also to complement the pre-existing satellite information, particularly within the coastal region when we already know we have no information. Also, this methodology will open new questions, new scientific problems to be implemented in the incoming satellite missions. Also, now that we are able, or we will be able to retrieve a total surface current from space in a bigger space domain, we can study and understand better transport processes. And additionally, we can use these methodologies as a complementary information for altimetry derived currents in the coastal region. For those who are interested in satellite missions, you can see the SWAT mission, which is the one which is going to be released in November, and is especially devoted to measure high spatial resolution surface currents. Particularly, the mission is going to start and will be measuring here in the northern Mediterranean Sea. Thank you, gracias, and well, if you have any questions, don't hesitate in asking.
Thank you, Alejandro, for your interesting presentation. If you have any questions, please leave them in the chat here in Teams, or if you are in YouTube or in Facebook, and they will copy them, the questions here in the chat, and we will ask them at the end of the 3 presentations. So if you can minimize, Francisco, your Teams, you can turn on your microphone, because we are looking at the Teams window.
Okay, can you hear me, Valeria? Hello?
Yes. Yeah, maybe if you share on, yeah, we can see you now.
And now you should see my screen.
Yeah, we are looking at but we are looking like the whole window, not with the tabs, not the.
And now?
Yeah. Well, I will introduce Francisco Criado. He's a PhD student in coastal engineering in the Federal University of Rio de Janeiro, with an MSc in coastal engineering. Since 2019, he's a technician of the beach monitoring facility at SOSIP, and before joining there, he worked as a research associate at the Laboratory of Dynamics and Cohesive sediments in the University of Rio de Janeiro. His research interests focus on coastal processes, beach hydro and morphodynamics, and he is currently working on beach response to sea level rise and storms. So I leave the floor to Francisco.
Many thanks, Valeria. And first of all, I wanted to say thank you for inviting me and having me here today, sharing what we are doing here at SOCIP. And yeah, it's a pleasure to still be in touch after this almost 5 years since our summer school in Puerto Morelos, and hopefully we see again in person. So I'm gonna speak about the Balearic Island Coastal Observing and Forecasting System, and more in detail about the beach monitoring facility where I am working. As Valeria said, I am Francisco Fabian. My colleague and head of the facilities, Ángel Fernández Mora, and Luis Gómez Puyol and Alejandro Fila started this facility with our director, Joaquín Tintoré. So let's get started with the presentation. I will go through this the following outline. Firstly, with a brief introduction again of the Balearic Island Coastal Observing and Forecasting System. Here and after I will say SOCIP. After that, I will explain in more detail the beach monitoring facility and how we work, about and how we use this modular integral beach monitoring system, which I will try to say as MOBIMS. I will also show you a brief GIF or animation about the BMON Viewer, which is an application we just launched a couple of weeks ago, and finalize with some applications or some analysis we are able to do with the data we collect in the summary. Okay. So again, the Balearic Island Coastal Observing and Forecasting System is an ICTS, as we call in Spain, which stands for Unique Scientific and Technical Infrastructure in Spanish. And it's supported by the Spanish Ministry of Science and Universities and the Balearic Island government. SOCIP is a multi-platform distributed and integrated system with 3 key drivers, which are science priorities, technologies developments, and response capacity to society needs. And on the top panel, you can see the different facilities who compose SOCIP. The first one on the left side is the coastal research vessel. We also have a facility of coastal high frequency radar. I'm sorry, Alejandro, but I'm not go deeper in about the coastal radar. It's another colleague. I will speak about the beach monitoring facility. We have also SOCIP has also a gliders facility, Lagrangian platforms, fixed station where we have sea level stations, weather stations, and buoys. The beach monitoring facility, which I will explain in detail in the next slides, and also an ocean forecast and modeling system. So with all these facilities together, SOCIP develops applications and operational tools for science-based management of the coastal and marine environment. Okay, now going to the beach monitoring facility. I have to talk about or to explain in detail the modular beach integral monitoring system, which we use at the beach monitoring facility. And this, before saying that, I wanted just to do a bit summary about the coastal system, which coastal systems are dynamic environments, as you already know, and many processes operate at different space and time scales. So understanding nearshore processes and the response of coastal system at all these scales is increasingly important in this global change in times, in line with our webinar, Facing Climatic Change. And for that reason, high frequency long-term data sets are key for this science-based management of the coastal zone. So we need data to properly manage our coasts, who are suffering with climatic change, this sea level rise, the storms are increasing in intensity and frequency, And for that, data again are needed. So now talking about the beach monitoring facility, we have, as you can see on the left on the map, we have actually nowadays 2 stations working, one in Cala Millor, which is in Mallorca, the bigger island, and the other one in Sombou. The red point is an older station who was working until 2017. And unfortunately, this isn't working anymore. And hopefully in September, if everything goes well, we will have a new one also in Mallorca. Now introducing the MOBIMS. This integral system can be divided into two different parts. The continuous measurements, which we have on the left panel on the top, and it's also coupled with the field campaigns. So talking about somehow the remote sensing part of this system, it's composed by a video monitoring system, a hydro, and a meteo measurement. The hydro is an ADCP who is installed on about 18 meters depth, and the weather station. Talking about the beach monitoring, the video monitoring system, we have, as you can see, this example is from Cala Millor. There we have 5 cameras. In this case, it would be similar to Sombou. We have 5 cameras who take images every hour, so that we get Sirena products image, which are the Timex, variance, snapshot, and time stack. These 4 image products. They are pretty similar, and you probably are more familiar with the Argus system. Sirena is similar to it, but the only difference is that Sirena was developed here, and it's an open source code, so it makes it cheaper to use it with, free. So once we get these images, an example is the plane view that you can see on the bottom. We correct all these images, we auto-correct this photo, generate this plan view, and with that, for example, we can extract shorelines. So we can see for example, the response of the beaches after certain energetic events, or see how our beach behave with this, only as an example of a product that can be used. The other one, as I said, is the AWAC, the ADCP. So we have a whole series, of wave parameters, and we have, I didn't say that, we are working, SOTHIP is actually working since 2011. So we have an uninterrupted time series since there, more than 10 years now. And the weather station, that's just an example of the time series of the weather station. Now continue with the field campaigns, the other part of this MOBIMS system. This MOBIMS system is, as I said, also we get information in situ, and we do twice a year. One of them before the summer and the other before the winter, with pretending to get the summer and the winter profiles or beach states. And these campaigns consist in a complete bathymetry with a multi-view echo sonder, and the topography, which we do working with the Arctic Ice GPS system. We join all this data and are able to generate these digital elevation models, so that we have 2 per year, and we can compare and see how the beach behaves in it. So also once a year we get sediments in different profiles, always in the same points, so that we have also measurements along the time of the same sediment variation. Okay, now I hope it works. This is the VMON viewer that we launched a couple of weeks ago. And here we can see the data from the Sirena system, the images, which is an app to make it friendly and easy to use. We can, for example, see easily the historical images, just choosing the station we're interested in the products we want to see, the Timex, for example, and we get the whole time series or for an specific date that we have interest. Another interesting tool of this app is the compare tool, which allow us, or it's actually also we thought also in all the users that it can be used for all kind of person, not only researchers, but everyone who is interested in and people who have to manage other beaches. So we can choose images of different dates, for example, and compare. And here we can see how the shoreline changed between 2021 and 2022 in Calamillo Beach, for example, in that date. And another tool I wanted to show you is the data discovery. And here the same, you can choose the station and you have access to all the wave data as well as the weather data. It's composed by an easy and advanced option, and the advanced option you are able to access and get information and select all the parameters. For example, here from the weather station, and the same with the AWAC. And here, just finishing, showing you this. For example, you can choose a period of time with a significant wave height, and you can see how the pictures were for that specific date pieces, snapshot, the Timex, or what you are interested in. So that's the BIMO viewer as a tool, and as I said, it's couple 2 or 3 weeks ago we launched it. And now just 2 examples of analysis we can do with our data or this kind of data. As I said, we have more than 10 years now, but also we have a high resolution data. So we can, with this high resolution data, we can study or analyze short-term scale events, as for example this one, which was a storm in 2020, a huge storm here for the Mediterranean Sea. So, and we are able, for example, to get on the left side, on the top on the left, we have the significant wave height and the peak period. And the third plot is the beach width, so we can relate the wave parameters with the position of the shoreline, for example. And we can realize, for example, that in the red line is when the storm arrives, and after that we see that the beach is narrower. Similar results on the third and fourth panel, where we see the beach width along the time and along the beach, and we can see in the middle, the center part, close to the zero, we have the beach is wider, and the south and the north part are narrower and suffering more. And we see that along the time, in this short period of time, we lose some beach, some width, or the beach was eroded. Also in the center, we have 3 plan views, which also represent with the red line the time, the shoreline before the event, and the green line the shoreline after it. So we can see some places where the beach was eroded, and some pictures of this particular event. And on the other side, we have this long-term scale data. 10 years are not that much, but we can start to think and to see some patterns along the time, some trends. So with the data, with the wave data, and for example on the right, on the top right panel, we have this shoreline position again on the second, and the significant wave related, and we can see that along a trend, erosion trend along this 10 years. And we can also see that after more energetic events, we have erosion at overbeach. Another kind of plot is in the left side, but talking almost the same. We have the green line is the shoreline in 2011, in red in 2020, and yeah, we can. And the gray part is the standard deviation. Yeah, and we see that how this particular beach lost a lot of beach width. So summarizing, MOBIMS from the beach monitoring facility and SOCIP is a low-cost system. We have this data open, and yeah, we develop this friendly applications as that one as I show you, between others. And we have I also have to say that we have all this data real or in near real time available. So you can just go to the website and find all this data, since the images to all the data we have measuring. And near real, I mean, for example, for the AWAC that we change every 6 months after we recover it, we process it and we uploaded it. So we have more than 10 years of high resolution data, which are, as I said, these image products, Timex, snapshot, time stacks, and variance. We have this wave and current data, weather data from the weather station, and also sediment information. So MOBIMS, this modular beach integral monitoring system, proves to be an effective tool to better understand our cost processes and provide key information for coastal management, which is already more and more needed in our times. So that's it. Thank you very much for your attention.
Thank you, Francisco, for your presentation. It's very interesting to see these efforts to monitor these beaches with your system. So if you have any questions, please don't forget to leave them in the chat. We will ask them at the end. So our next presenter is Talia. I won't try to pronounce her last name, but she is a civil engineer with a master in port and coastal engineering from South Africa, and she recently submitted her PhD dissertation in Germany. Her PhD focuses on step revetments for coastal protection, and she has research experience that includes physical model tests to study wave structure interactions. Talia, can you share with us your screen?
Yes, just a minute.
Yes, now we can see you.
Okay, can you hear me also fine?
Yeah, fine.
Just
Yeah, now we can see your presentation.
Okay, perfect.
Yeah, thanks.
Thank you for the introduction. I will now tell you more about step revetments as sustainable coastal protection. Oh, sorry, I had the wrong screen. Okay, perfect. With a focus specifically on hydraulic and environmental design aspects of step revetments. And with sustainable coastal protection, I mean coastal structures that balance social, economic, and environmental needs while retaining their primary function of providing coastal safety. This presentation gives an overview of the main findings of my PhD research. Sorry, there's sort of a delay going to the next slide. Okay, firstly, an outline. I will start off by giving an introduction about what step revetments are and their functions. And I will explain more about the research motivation and objectives. Thereafter, I will give an overview of the hydraulic design aspects of step revetments, and these aspects I researched through physical model tests. Thereafter, I will give an overview of environmental design aspects of step revetments that can be taken into account to design these type of structures in a more sustainable way. And then I will end off with recommendation and conclusions. Step revetments are shore parallel stepped slopes designed to protect the coastal inland from flooding and erosion. The revetment stairs dissipate and reflect part of the incident wave energy. Step revetments can be designed to be multifunctional, which make them particularly suitable in urban areas or in coastal cities. They can be designed to have recreational benefits. For example, as in the picture shown, they can provide safe access to water areas or incorporate walkways. Step revetments can even be designed to have a high cultural value by incorporating art installations, such as here in the sea organ in Croatia. As waves run down, up and down the structure, they create sounds, and this creates attracts a lot of tourists to the promenade. As waves interact with a step revetment, part of the wave energy is reflected from the structure. And this is known as wave reflection. And as the waves interact with the structure running up and down, the flow is interrupted by the revetment step, creating turbulence and causing energy dissipation. As a result, wave run-up and overtopping are reduced in comparison to a smooth slope or dike under the same boundary conditions. Wave run-up is defined as the vertical distance between the still water level and the highest point of wave run-up. And when the wave run-up height exceeds the crest height of the structure, wave overtopping occurs. And this is when water is discharged over the structure crest. Although there are numerous examples of step revetments and over 70 years of research on the topic, there are still persistent knowledge gaps. Previous full-scale model studies have shown that step revetments effectively reduce wave run-up and overtopping compared to smooth slopes or dikes. However, there is still significant variability in the hydraulic responses under the same boundary conditions. Therefore, it makes it hard to derive general design recommendations, and these are not yet included in design manuals. Furthermore, it is uncertain how scale effects influence the small-scale measurements, and the hydraulic processes on step revetments are not yet fully understood for a large varying range of boundary conditions. And lastly, environmental aspects are not yet included in standard design practice. The research objectives of my PhD was to improve and supplement hydraulic design recommendations, specifically for wave overtopping, wave run-up, and wave reflection. And secondly, to identify environmental aspects that can be considered in the design of step revetments in a more sustainable way. These objectives I also go through in the presentation today. And the first objective is addressed through physical modeling, whereas the second objective was research based on literature review. Firstly, I will give an overview of the hydraulic design aspects for designing step revetments to offer coastal safety. We conducted physical model tests in the large wave flume in Hanover, Germany. The flume has a length of around 300 meters. It's 5 meters wide and 7 meters deep, making this a large-scale test facility. And we tested 2 model configurations. We selected a slope of 1 to 3 so that it would be representative of a German dike cross-section, where around the coast of Germany, dike slopes on the seaward side typically range between 1 to 3 and 1 to 7. But because step revetments are often built in cities, we wanted to select the steepest slopes to also limit the footprint of the structure. We tested the 2 model configurations. The first one had step heights of 0.5 meter. The step height was selected so that the steps can also serve as a place to sit or serve as a bench. Whereas the smaller step height of around 17 centimeters was selected based on a typical height for climbing up a staircase. The generated waves had a significant wave heights up to 1 meter and wave periods up to 6.5 seconds, which is representative of wave conditions around the German coast. The water depths in the flume range between 4 and 5 meters, and incident wave conditions were measured with 2 arrays of wave gauges that measured the surface elevation from which the incident and reflected waves could be determined. On the structure itself, from these measurements, the wave run-up height could be determined. In the event that the run-up height exceeded the crest level of the structure, water overtopped, and the overtopping water was guided through a channel into the overtopping unit, and this overtopping unit was placed on 4 load cells that measured the weight of the water, and from this the wave overtopping could be determined. The next slide shows a video, I hope it shows well, with the waves running up the larger step revetment with 0.5 meter step height. And as you can see, there's a lot of splash ups occurring and a lot of aeration in the water. The next video shows overtopping events at the smaller stepped revetment with 17 centimeter step heights. It was found that step revetments effectively reduce wave overtopping, run-up and reflection compared to smooth slopes under the same boundary conditions. This reduction was also quantified, and for that empirical formula were derived. Firstly, to estimate the roughness factor for stepped revetments that can be applied in combination with the Eurotop manual's overtopping formula. In other words, with this roughness factor, you can apply the Eurotop formula to estimate the wave overtopping rate for stepped revetments. And also an empirical formula was derived for the reflection coefficients and the wave run-up. The wave run-up and wave overtopping are both important for the crest level design of the structure. In other words, how high the step revetment has to be to obtain a certain level of coastal safety. Furthermore, the comparison between the two tested model configurations, it was found that the largest stepped revetment with 0.5 meter step heights was more effective in dissipating wave energy. Therefore, the smaller steps has higher relative run-up heights, whereas the small steps experience 55% higher wave reflections than the large steps under the same boundary conditions. Also, in terms of wave overtopping, the large steps were more effective in reducing wave overtopping compared to a smooth slope than the small steps. To compare the full-scale model test with previous small-scale studies, it was found that the small-scale measurements are likely affected by scale. This was found for wave overtopping. Previous small-scale predictions underestimate the roughness factor of step revetments by 2 to 31%. Whereas relative wave run-up heights are also underestimated in the order of 31 to 51%. This means if you would base your crest level design of step revetments on these previous small-scale prediction, it could lead to unsafe designs, making the structure lower than it is supposed to be for the certain level of design level of coastal safety. Therefore, care should be taken if you want to base your design on small-scale measurements of step revetments, and you should account for the scale effects in your design. And next, I will give an overview of environmental design aspects for designing step revetments in a more sustainable way. Step revetments are designed to offer coastal safety, and therefore they form a barrier and bring changes to coastal processes. However, this also brings unintended negative environmental impacts. For example, they bring changes to the sediment dynamics in 3 different ways. Firstly, a portion of beach is lost due to the construction of a step revetment, and this is known as placement loss. And when step revetments are built on shorelines that experience net long-term erosion, the beach erosion will continue in front of the structure, causing the shoreline to retreat towards the structure. In the case of the step revetment would not be there, the beach width would remain mostly the same and move further inland, but the step revetment blocks this process from taking place, and thus leading to passive erosion. Furthermore, step revetments also affect the sediment processes in the longshore and in the cross-shore direction. Firstly, due to wave reflection from the structure, this could lead to scour at the toe of the structure. And in the longshore direction, it could lead to accretion on the updrift side of the structure with downdrift erosion. These erosion problems also lead to ecological impacts, such as firstly due to loss of habitat. This is due to the erosion that takes place, and also as the construction of the structure influence the habitat. Step revetments not only form a barrier against wave action, but it also brings a barrier to species. And this thing affects the ecological connectivity of the system. Movement between the backshore and the beach is essential to species, for example, for seeking refuge or for nesting purposes. Step revetments are mostly constructed of concrete, therefore they introduce new hard material into the system, creating new habitats and bringing changes to habitats. And also the concrete surfaces are notably smoother than natural habitats. These new habitats that are created are often colonized also by invasive species, as they bring new type of habitats into the system. Certain adaptations can be made to the design of step revetments to minimize environmental impacts or to retain and create ecosystem services. The feasibility and success of these adaptations depends on the local conditions, such as the ecology, hydrodynamic and spatial requirements. Therefore, these adaptations are not a one-size-fits-all, and this requires also some knowledge of the local environmental conditions and interdisciplinary collaboration between professionals. The first type of adaptation that can be made is to mimic local habitats as closely as possible. An example of this is when step revetments are built on coastlines where naturally rock pools occur. Water retaining features can be incorporated in the revetment steps. Furthermore, as smooth surfaces are poor surrogates for intertidal habitats because of their homogeneous smooth surfaces. Another adaptation that can be made is to create a range of habitats by maximizing roughness. This can promote higher biodiversity compared to smooth surfaces. Furthermore, step nourishments can be applied in combination with step revetments to address the effects of erosion and habitat loss that is associated with erosion. The position and the geometry of the step revetments are also impacting the type of environmental impacts that take place. For example, the position in the intertidal and also the geometry in terms of the step height and also the slope of the structure. To preserve or restore ecosystems in the foreshore of a step revetment, ecosystems can be restored, and this can create new ecosystem services, and this could also have a positive impact on the coastal safety as wave, for example, wave attenuation that can take place, that lower wave heights are reaching the structure. Lastly, to avoid the over-design for future worst-case scenarios, flexibility can be built into the design, such as when we later better know how to predict the sea level rise, we can expect the height of the structure can be increased at a later stage. So also allowing that you can build the structure or the protection measure in increments. Sustainable coastal structures balance the future social, economic, and environmental needs. And this includes the effects of climate change and sea level rise. This has to be allowed while retaining the primary function of coastal structures, that of providing coastal safety. It is recommended to consider environmental and social aspects from the earliest design phases. This allows coastal engineers to optimize their designs and also being aware of the impact that coastal structures have on the environment. Step revetments have been shown to be effective coastal protection. This was quantified with the full-scale model tests that were conducted, and they offer unique opportunities for ecological enhancement, for example, mimicking natural habitats on their vertical and horizontal step surfaces. The multifunctionality of step revetments make these structures especially suitable in urban and touristic settings. The presentation is based on the following publications, and these are my references that I included. And I would like you to thank you for your attention and for listening.
Many thanks, Talia, for showing us your research. Very interesting in regard of coastal protection challenges that we are facing. So we have some minutes to ask some questions that we have here in the chat. So Alejandro and Francisco, if you are there, we have here one question for Alejandro.
Yes.
Victor asks, what is the main challenge to achieving the merge of data?
Okay, so I would like first to, before answering that question, I would like to expand a little bit more the question regarding the answer that I gave to Rodolfo, because when he started to ask, I straight away started to answer, but I forgot that it's better to do it by this way. So first, if it is okay, I would like to answer this question. So, well, Rodolfo, actually, yes, when you're estimating the surface, the surface geostrophic currents, basically the geostrophic currents, particularly from satellite informations, you have to estimate two things. You need to have the sea surface height, which is basically the variance of the main position of the surface of the sea. But in addition to this, you need to have the mean dynamic topography, so which is basically a reference value with respect to the curvature of and also the datum of the planet. So yeah, you need initially to estimate these two values, and according to this, you superpose these two values, and you use all the information, all the sea surface height you can have from several satellite systems, and then you can do a spatial interpolation to have a gridded geostrophic currents from the satellite information. Well, and for Victor, thank you also for the question. So basically, one of the, data mining is quite complex, because when you are using any kind of data mining learning processes, the main problem, maybe you know, the people here know that already, is trying to make the information you are trying to present to the neural networks or any kind of these learning processes readable for the input, as an input for the neural network. So if you are especially using information from several data sources, one of the main things is initially to put everything in a consistent way. Let's say time resolution, space resolution, but in addition to this, always the gaps, because I guess all of you guys, for example, Francisco, when you're analyzing information at the coastal region, we know we have a lot of time, many gaps. Sometimes the equipments are not working. Sometimes one equipment is working and the other one is not working. So when you have information from one equipment, you maybe don't have information from the other equipment. So it's quite picky sometimes when trying to merge information. But generally, what you have to do initially when you are trying to merge the information is, or the data, is try to put everything in the same temporal resolution and in the same reference system, and after that, the tool or the learning process you are using for sure is going to let you know what else you are missing. And yeah, it's that, I guess. I hope I can answer the question then.
Thank you very much, Alejandro. We have here a question for Francisco. Says, what do you think, from Eric, what do you think of monitoring efforts that use photos taken by locals and tourists, like GhostSnap?
Yeah, thank you, Eric. Yeah, it's thank you for the question. I actually have here the cradle of the GhostSnap. Mm-hmm. We were actually, my Angels, who is responsible for the facility, was almost fighting for because we choose 2 natural parks to install this these CoSNAPs, and yeah, natural parks and bureaucracy here is very hard. So yeah, we are after almost 2 years this week, yesterday or the day before, all the stuff arrives, and hopefully in 2 weeks we are gonna install our 2 first stations here, the Balearic Islands. And yeah, we follow all this work of the team of Harley in Australia, and we think it's a very interesting tool and more for, because it would be nice to install such a modular system, a moving system as we have in the station, but there are many places and a lot of beaches where we don't have access. So it's nice to have at least some CoSNAP station where we can get some interesting information, at least shorelines with these smartphones. So yeah, it's a program we think is very interesting and worth it.
Okay, thank you, Francisco. We have here for Talia, John asks, from a practical perspective, how do you ensure during construction that space is created landward of your step revetment for future expansion?
That is a good question. So I think the main thing is to take this into account from the beginning when you start a management plan for if you design a coastal structure or a management plan. So if you would increase the structure further at a later stage, that is to allow in your design already from the beginning space so that you can increase it at a later stage. So I know around the coast of Germany and also in the Netherlands, they do these type of designs that they leave space so that they can later on increase the height of the structure. But I mean, of course, when it's in a coastal city where the demand of space is limited and it's a high demand of space, that is of course not always possible, and then you increase your structure and that also affects the line of sight to the beach, and so there's a lot of different factors to take into account.
Okay, thank you. Well, Alejandro says that he has a question. Alejandro, if you want to ask Talia, for Talia.
Yeah, for Talia, thank you, Talia, for the presentation. It was very nice. So I would like to ask you, I know you were basically showing us a very interesting research regarding very hard structure, coastal defense structures. However, I would like to ask you if you have any knowledge about the comparisons between natural-based solutions, for example, the mangroves and the aquatic vegetation you were introducing at the very end of the presentation. I mean, in terms of efficiency. So because nowadays in other places, particularly tropical places, they are trying to move from hard man-made structure to natural-based structure. So what do you think, especially in the Northern Sea, where we have very strong tides, very strong waves, and very strong weather forcings, how efficient should be this change, this migration to structure?
Yeah, that is a very good question, and I think a lot of dilemmas going into that, and a lot of research also. For example, in the North Sea, they also look a lot of salt marshes, for example, building out the salt marshes in front of the dikes, which could also lead them to hybrid solutions that you incorporate that with the dike design. But although there are a lot of ongoing research, there are also a lot of uncertainties due to the natural nature-based solutions. For example, seasonality, that also plays a role, and also you need a lot of space normally to obtain the wave attenuation that you would need.
Okay, thank you, Talia. I received a question from somebody that is watching on YouTube. Deborah asks, what's the minimum equipment to replicate a monitoring effort similar to a new beach? This is for Francisco.
Can you say again the question, please?
What's the minimum equipment to replicate a monitoring effort similar to the one you are doing in a new beach?
Well, the minimum, as I said before, with the CoSNAP, having at least photos is some information. But yeah, the interesting thing in our station is that we can have The morphodynamic information we can extract from the for the shoreline, for example, through these images, and we also have information of the waves due to this IDCP we have installed there. So and a weather station. So yeah, I think it's a difficult question. If you could have everything, it would be better. But if you can have information of the wave condition and the morphodynamic response of the beach, it would be nice. I mean, it was enough to do some research and to understand better how the beach behaves.
Okay, thank you. Well, so we have one more question in the chat, but I think we just have time to close this webinar. And actually, Andreas has his hand raised, and I was going to give the floor to him also. So, Andreas, if you want to take the floor, please. You can turn on your microphone and camera. I guess we can hear you. I guess you have your microphone turned off.
On now?
Yeah, we can hear you now.
Great. Okay, yeah, my name is Andreas Hafstrick from TU Braunschweig, and I would like to ask Talia one question. I'm not a coastal engineer, I'm more a bioengineer, but what I would like to know from you is, I know the background is to break the power of the waves and to take them the energy. Is there any optimal step height of the revetments where you say, okay, 0.5 meter is the optimum, or is there still a wider range where you say this is the optimum step height where I can take the power or can break the power of the waves?
Yes, that is also a good question. So what determines this optimum step height is also based on the wave conditions that you will have. Okay. And my colleague that studied step revetments before me studied them in small scale, so he had the ability to measure a wider range of different types of configurations in terms of step heights and wave conditions. And he did identify a more optimum height that depends on also the incident wave conditions.
Okay, thank you.
Yeah. I cannot tell you that right from my head, but yeah, there is. That's a good question.
Thank you, Talia. So, Andreas, I don't know if you want to give us some words before Elvis, so that you have.
How much time do I have? 2 hours or? No, I don't want to extend as necessary. Yeah, thank you very much for giving me the floor. And as I said, my name is Andreas Hafstrick from TU Braunschweig, and I would like to thank, first of all, you, Valeria and Rodolfo, and also unknown friends and colleagues behind for the organization of this webinar. And we have a kind of webinars, a number of webinars over the year, where we are organized in a network that is the Exceed Swindon network. Would like to mention this, and some colleagues agreed in organizing webinars over the years. And one of these webinars is this, organized by UNAM. And others will be organized in the MENA region, in Southeast Asia, and also in Sub-Saharan Africa. So I can tell you we have each month, I organize 2 or 3 webinars with colleagues from these regions. So thank you very much, especially to you, Valeria, and Rodolfo, for this very nice webinar. And I learned a lot as a bioengineer. I'm also very impressed about the tools you have available. Meanwhile, all this satellite technique in order to get very useful data from space in order to validate your models. I think, yeah, that will be the future. And we know that from UN Water, for example, because the topic of this webinar is also sustainable and the protection of coastal areas, especially where we have this mega city and coastal areas. And we know from UN Water that by 2050, I guess, 300 million people will be affected by annual floods. And that is not only in inland, that is also in coastal area where we have these estuary areas, where we have these deltas of rivers. And the EU recently published in its Atlas of the Human Planet 2020 that 3/4 of the world's population now live in large cities. This is currently corresponds to 5.6, imagine, 5.6 billion people worldwide. So there you can see, of course, as coastal engineer, you know this problem, you're aware of this. What does this mean in future because of climate change and sea level rise? So there we are coming a lot of huge and severe problems, starting from destruction of coastal areas, going to problems where we have saltwater intrusions into coastal aquifers, and the urbanization. These big cities, they will expand. And what does this mean to the ecosystem around? And in addition, we destroy mangrove areas, we destroy coral reefs. Okay, I don't want to continue here. We know all these problems, and therefore it's very important to know something about what in the future, if there will be sea level rise and many other disasters like hurricanes and so on, what will happen with coastal areas, and especially with these mega cities. We have many of them, especially in Asia, in coastal areas. And one last number, we know from projections and from numbers collected by UN that in the next 10, 20 years, more than 3/4 of world population, 3/4 of world population will live in megacities. And then you can imagine what this will mean to the environment and to how to protect these megacities when they are in the coastal areas. So there's a lot of things. There are a lot of things to do, and I think the reaction time is very short. Meanwhile, you know, in the context of climate change, and it's getting shorter and shorter. And a relocation of megacities like Jakarta, you know this example. Is that a solution? Well, I think this is more or less a rhetorical question. I think we know the answer for ourselves, what to do in future, but time is getting shorter and shorter. I don't want to paint the devil on the wall, but I think we have to face these problems in the future. Thank you.
Many thanks, Andreas. We have here another question that have been. Well, we have a comment from Marco. He says that thank you for the webinar. That an idea for he proposed is talking about risks in urban areas near the coasts, like for example in Cancun. That is an example of cities and coastal risk. At least here in Mexico is one of the main coastal touristic destinations, so it would be very interesting. And well, I see here another question for Talia, from John. He asks, in what conditions can you install seagrasses or mangroves or some other ecosystem approaches with reference to your third adaptation option to reduce scoring effects on the foreshore?
Firstly, it depends on what type of ecosystems naturally occur in the area you are focusing on. So where you want to build your state revetment. And then, for example, this would depend on what hydrodynamic conditions, so what type of waves and sediment conditions you have in front of your structure when you decide how to incorporate those. So there is some research on hybrid solutions, it is called, if you combine hard structures with nature-based solutions or ecosystems. So there are some research on that.
Yeah, and I think the last one is another one also for Talia from Rodolfo. He asks that in terms of design criteria for structures, how do you think it is possible to balance changing societal needs versus the value we place on coastal ecosystems and the design for risk of structures necessary to meet human needs and wants?
That was a long question, but also a very important one. So I think this calls also for a lot of education and telling the type of what influences coastal structures have, and also the type of benefits you could have from the ecosystem services that restoration of ecosystems will be providing. And it will also go into political, yes, in the politics, that it has to be included into legislation and so on.
Okay, well, many thanks. So I guess there are no more questions in the chat, so I will give the floor to Elvis. I guess you should also have the permissions to turn on your camera and okay, well, thanks.
Hi, Elvis.
Hi, can you see me now?
Yeah.
Okay, so today it was a very inspiring moment. I had the opportunity to learn a lot with you all. My name is Elvis Carissimi. I work in southern Brazil, mainly with wastewater treatment, so I'm not a coastal engineer as well. But today it was a great opportunity to learn a lot about the challenges regarding climate change and coastal areas. That is the special region where people prefer to live. In Brazil, we are recognized as a continental country, and the majority of the people, I mean around the 8% of the population, prefer to live alongside the coastal areas than in Pantanal or in the Amazon region. I myself, I live in land with the rest of the 20% of the population, but I confess I miss the beach. But we know that the challenges are very big, and so we need to have research, we need to search for solutions, and monitor the waves and everything you talked about to try to transform the coastal areas in a sustainable place. So in the frame of the Swindle Water Association, I also would like to congratulate and invite the speakers, Dr. Alejandro, Dr. Francisco, and Dr. Talia, for the inspiring speech and for sharing your research with us today. So thank you all so much. Thank you, Valeria and Rodolfo, for organizing also this special webinar. Thank you so much.
Well, many thanks for your words, Elvis. So I guess, well, we will finish the event. Many thanks for all the assistants here in the Teams and Facebook and YouTube. And well, we hope to see you in the near future in another webinar. So thank you all.
Thank you.
Thank you so much.
Thank you.
Thank you. Bye bye.
Okay.
See you.
Bye, Elvis. Bye, Rodolfo.
Bye.
Thank you. Bye.